Since linear approximation is an estimate, we often want to find how accurate our estimate is, or to figure out rather how inaccurate it is. So we try to find the error. To help with this are differentials dy and dx. Now typically when we've seen dy and dx, we've seen dy dx. And typically when we've seen delta y, we've seen delta y over delta x. So the change in y over the change in x. So we've usually seen this as if we're looking at the slope between 2 points, where we have the change in y over the change in x. Now we're going to start splitting this up so we can look at specifically the change in y, or specifically the change in x. So if we have x is equal to some value, and we increase x by a particular amount, so we add the change in x, delta x, then we can figure out the change in y that corresponds to that change in x by finding f of x and finding f of the quantity x plus that change in x, where the change in y is the distance between those two. Now, differentials are differences that are infinitely small, or infinitesimals. So this has to do with instantaneous differences. This dy is equal to f prime of x dx comes from if we have y is equal to f of x, then when we take the derivative of this, this is equal to dy dx is equal to f prime of x. And we can solve for that differential dy by multiplying both sides by dx. So we get that dy is equal to f prime of x dx. And this is the process that we'll use in order to find the differential dy. So if we need to find dy for f of x is equal to sine cubed x, first we want to rewrite this so that we have y is equal to sine cubed of x. And since we need to take the derivative of this, we want to rewrite this so that we can use the chain rule. So we have the quantity of sine of x cubed. Now we can take the derivative. So we have that dy dx is equal to 3 times sine of x squared, using that power rule. Then we have to take the derivative of the inside function sine of x, so times cosine of x. Then we want to solve for dy. So we multiply both sides by dx. So we have that dy is equal to 3 sine squared of x cosine of x dx. Now let's get some practice computing the change in y and dy for given function values. For this example, it's very important to note that we're saying specifically that delta x is equal to dx. These things are not always equivalent, but in this case, we're looking at where they are equivalent. So here, f of x is equal to x squared minus 2x plus 3. X is equal to 1, and delta x is equal to 0. We have that delta y is equal to f of x plus delta x minus f of x. So delta y is equal to f of the quantity 1 plus 0.1 coming from the given values minus f of 1. So we need to find f of 1 1/10 minus f of 1. So we'll need to substitute into our function twice. First to find f of 1.1. So we have 1.1 squared minus 2 times 1.1 plus 3 minus, now we'll find f of 1, which is equal to 1 squared minus 2 times 1 plus 3. So we have 1.1 squared, which is 1.21, minus 2 times 1.1, which is 2.2, plus 3, minus 1 minus 2 plus 3. (1.21 plus 3 is equal to 4.21. Then we're subtracting that 2 into tenths, which I'll rewrite as 2.20, minus 1 minus 2 plus 3 gives us 2. 4.21 minus 2.2 gives us 2 1/100th. Then we still need to subtract 2. So we find that delta y is equal to 0.01. Now we still need to find dy, that differential, where dy is equal to f prime of x dx. The derivative of our function with respect to x is equal to 2x minus 2, just using the power rule. So dy is equal to the quantity 2x minus 2 dx. I wish it wouldn't do this. Substituting in the values that they gave us for our problem, we have 2 times 1 minus 2 times dx. They said that dx is equal to delta x, which is equal to that 0.1. So dy is equal to 0 times 0.1. So dy is equal to 0. Now we'll look at how to use our differentials in order to find error. So for this problem, the radius of a circular disk is given as 14 centimeters, with a maximum error in measurement of 0.2 centimeters. We want to use differentials to estimate the maximum error in the calculated area of the disk. We also want to find the percent change of the area. Let's start by listing what we know. We know the radius, which we will call r, is equal to 14 centimeters. About. With some sort of maximum error of the measurement of the radius, which we call dr, so some maximum difference of 0.2 centimeters. We want to find the error for the area. We know that area is often called A, and that the formula for the area of a circle is equal to pi r squared. we're trying to find the maximum error of the area, which will be equal to dA, but we're not quite sure what that is. The area is a function of the radius, so we know that A is equal to that pi r squared, and we can find the derivative of the area with respect to the change in the radius. So we have dA dr is equal to 2 pi r. Then we can solve for that differential dA by multiplying both sides by dr. So we have that dA is equal to 2 pi r dr. For this problem, we know that 2 pi r will be 2 pi times 14, and they gave us that dr, that difference for the area, is a maximum of 0.2. So this is 2 pi times 14 times 2/10. So that's 2 times 14, which is 28 times 2, is 56 over 10 pi. So dA is equal to 5.6 pi. And that is the maximum error for the calculated area. Now we need to find the percent changes. Let's start by finding the percent change of the radius. The percent change of the radius will be equal to the change in the radius, dr, over the radius, r. So this will be equal to 0.2 over 14. But we need to find the percent, so we have to convert this to a decimal. I find it a little easier to first make it so that everything's an integer, so I'm going to multiply the numerator and denominator by 10. So I have 2 over 140, which is equal to 1 over 70, which is about, which is 1 over 10 times 1 over 7, which is approximately 1 over 10 times 0.141414, and so on. So that is approximately 0.014. So we have about a 1.4% change. Now we have to find the percent change of the area. This will be equal to dA over A, which is equal to that 5.6 pi that we found earlier, over A. So we have to find the area when the radius is equal to 14 centimeters. So that will be equal to 2 pi times 14 squared, which looks very, very similar to that 2 pi times 14 from earlier. So instead of writing 5.6 pi, I'm going to write that 2 pi times 14 times 2 over 10, which makes this a little easier to simplify. So our 2 pi's will divide out, and one of our 14's will divide out. So we're left with 2 over 10 times 1 over 14, which again gives us 2 over 140. Which is about a 1.4% change.